All right. This next group problem solve, I'm sure you could do. Come check your solution once you try it out. We've got 60 degrees is the instant they want us to look at and figure out how fast its angular velocity is, omega. So we've got to figure out, right? Maybe this is like a bridge lifting mechanism. As we actuate it with this cylinder, this hydraulic cylinder here, whatever it is, how much does that change this angle theta? Now that angle might be a little harder to get to, but I definitely see a triangle in there, right? So we could relate S to this angle at C just using log cosines. That's no problem, right? So let's do that. But if we want to relate it to theta, we just got to do 180 minus theta, right? Would be that inside angle at C. So there's this side squared equals that side squared equals that side squared, right? That's our cosine, law of cosines. These are our two opposite sides, and then AB is opposite of the angle C, which is 180 minus theta. So if we plug in what we know, which is the 3 and the 5 meter sides, which are constant, and we plug in the 180 minus theta for that opposite angle, we get the relationship that we needed, right? Between S and theta. And that is the magic equation that we can use. We can take time derivatives. We can get everything we need. So let's take a time derivative. And if you remember from the other example where we had a similar situation with an s squared on one side, a lot easier to take the time derivative of both of those than it is to square root it and have a bunch of chain rules, right? So just leave it as s squared and take a time derivative of both sides. So if you take a ddt of s squared, you would get 2s, but then s is a function, so we have to do the time derivative of s, which is s dot. You could also make that a v, whatever you want to do. And then the time derivative d dt of the right side. 34 becomes 0. 30 cosine theta becomes negative 30 sine theta. But cosine theta, theta is a function inside of the cosine function. So that triggers a uh, chain rule. So we've got to multiply it by the inside function time derivative, which would be theta dot. And theta dot's what we're looking for. So let's go ahead and solve it for that, right? That is omega, theta dot. So I'm going to rearrange this equation so that as long as I can go find s, s dot, and theta, we can plug it in and we're done. So let's try it. We know theta. We know s dot. They gave us those. Do we know s? Well, maybe we could solve for it when theta equals 60 degrees. Because, yeah, we did have a relationship between s and theta here that we got a second ago. So perfect. Plug in 60 degrees here, solve for s, you get exactly 7 meters. Nice. Now we've got everything we need. Plug in theta, s dot, and s into that equation, and we've got 0.0808 radians per second. And that's all there is to it with that one. So like I said, these ones, not overly complicated. It's just coming up with what is that relationship using geometry or trig or whatever it is to relate the linear to the angular. Once you've got that geometric relationship, bam, it's just calculus. Just make sure you don't screw up your derivatives or your chain rules or anything like that, and you'll be in good shape.